Okay. All right. Okay. So, ladies and gentlemen, we are now quite deep into this module on organic structure and naming. Right. So we've done alkanes, alkenes, alkynes. We've done branching. All right. We've also done haloalkanes, haloalkenes, and haloalkynes. So we've added an halogen. Right. We've looked at alcohols, and I've given you homework on carboxylic acid. So let's just quickly go through the homework. Today, I want to give you a more complicated problem that I want you to, a compound that I want you to name that's going to integrate several things we've already done. And it's going to be in a module, in a model form. Okay, I'm going to pass it around. If you want to, you can take a photograph of it, and then you're going to have to name it. Right, and then I want to move on to aldehydes and ketones, which is pretty easy. And then next week, we can start looking at esters, which are really very important. Okay, once we've done all of that, if we still have time, we can then look at past exam questions on this particular section. Okay, so methanoic acid. All right, meth, one carbon. We've got one carbon, right? Double bond O, OH, right? And then using the circle test, 1, 2, 3, 4, there's going to be a hydrogen there, right? If we see from left to right, HC, HC, double OH. Okay, what we call this, we call the Cu group. We phonetically we spell it like that, but of course it's obviously got an H in it. Okay, think of Cu, you know, the canned pears and what else does Cu make? Yeah, that stuff. Okay, ethanoic acid. Ethanoic acid is going to have two carbons. The F tells us two carbons. All right, C double bond O, OH. Okay, right, and then it's this carbon needs 1, 2, 3, 4. Right, this is going to be CH3 Cu. Right, now remember we've spoken about an homologous series. Can you recall every compound in an homologous series? As you start meth, then you do eth, then you do prop. What amount of carbons and hydrogens do you add? CH2. You add CH2. So the next one, meth, eth, prop. So it's going to be propanoic or propanoic acid. That really doesn't matter how you pronounce it. Propanoic acid. That's going to be 1, 2, 3. C double bond O. H. 1, 2, 3, 4. Right, so we add two hydrogens there. 1, 2, 3, 4. We add another 3 hydrogens there. Now note something. Can you see that we've added a CH2? We've added a CH2 in the series. So here you've got CH. Then by adding a C, all right, that H is there. We've added a CH2. And now we've added another CH2. And that's why in the definition of homologous series, it speaks about the fact that they differ from each other by CH2. Right, so there we go. The condensed structural formulae is going to be CH, apologies for that, is going to be CH3, CH2, COOH. CH3, CH2, COOH. Right, then, what is the next organic acid in this series? Butanoic, okay? So this is going to be butanoic acid. Right, so this is going to be 1, 2, 3, 4, C double bond O, OH. Right, so let's just explicitly look at the number of bonds around carbon. 1, 2, 3, 4. Remember the sp3 hybridization? Carbon sits in group 4, it's got a valency of 4. Eh? Oxygen sits in group 6. So it has a valency of 2. Why? Because hidden in here are, I'm just refreshing your memory, are 2 lone pairs. So it's 2, 4, 6, 8 around in the valence shell of the oxygen. Right, oxygen's got a valency of 2. Right, then we've got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now, when it comes to the condensed structural formula, CH3, CH2, 2, because there are 2 CH2s in that compound.
I forgot to mention this, but if you don't like as an absolute shortest form,
it's still fine. Good question. All right, a good question. Still acceptable. If you wrote CH2, CH2, and we asked you for the condensed structural formula, still fine.
Can you write 2 CH2?
No. No, you can't. It's also a good question, but you can't. Okay?
Is there one that NSC prefers over the other? Because with the naming, you said they
We give you either or. Either or.
Okay.
All right. What we can do is give it to you in this form and then ask you what compound it is. But if we ask you to do condensed structural formula, you can use either or. You could either do CH3, CH2, CH2, and then C the coup, or CH3 like this. So at the end, right, we've got, apologies for that, is the coup. But what is really important is you must explicitly keep the coup group as COOH. Okay. Now, the last one is pentanoic acid, right? I'm actually not going to do it. It's 5 carbons. It's going to be CH3, CH2, 3, COOH. You can give that one a go. Okay. Will you've done the homework. Now, what I want to do now is I want to pass this around. And the reason why I'm doing this is because when we present this to you on a 2-dimensional piece of paper, it looks different to the way it looks in 3 dimensions. Right, so this little green sphere here is chlorine. All right, so I'm just going to, for the sake of the recording, so just to show you, this is what it looks like. Right, and then there is a chlorine there. I'm going to pass it around. You're welcome to take a photograph of it. And ideally would prefer you not to communicate with each other initially. Give it a go, and then you can communicate you can do your peer-to-peer comparison. Okay, take a photo and pass it on. Right.
What is the red?
What is the
red? Oxygen.
The red is oxygen. So the black sphere is carbon. Right, the black sphere is carbon. It's fine. It's fine. You haven't even seen it yet. Where? There. You got good eyes. You got very good eyes, Declan. All right. I want you to actually hold it in your hands, and I want you to twist it. I want you to feel it. I want you to get a feel, the actual feel of it. Dimensional model, and I want you now to try and name it. I'm not giving you a diagram. I'm giving you a 3-dimensional model of the molecule. Right. So please take a look at it. The black spheres represent carbon atoms, right? The white spheres represent hydrogen. The green sphere represents chlorine, and the red is obviously oxygen. When you number a carboxylic acid, the Cu group's carbon is always carbon 1. The same will be true of aldehydes when we do aldehydes as well. Okay, so your Cu group is going to sit on the end. That's carbon number 1.
Well, that's called, the Cu group is called.
The Cu group, that is going to be carbon number 1. So if we have substituents in here, that'll be 1, that'll be 2, that'll be 3. This is 1, 2, 3, 4. Very, very important. So if we look at the longest chain must include, I'll draw it like this. Okay. The longest chain must include the carboxyl functional group and the halogen. All right. So this is 1, 2, 3, 4. This is going to be butanoic acid. Right, so it's meth, eth, prop, but. So this is going to be butanoic acid. That is the main backbone. And there's your C, double bond O, OH. Now, we number as follows. This is carbon 1. This is carbon 2. That's carbon 3. And this is carbon 4. Now, we can clearly see that here on carbon number 4 is a chloro. But sitting at the back here is a methyl. Sitting at the back is a methyl. Sorry about that. So there is a carbon and 3 hydrogens. So that's a CH3, which is a methyl. And it's sitting connected to carbon 3. So this is going to be 3 methyl. Now, as Taylor was asking, how do we now construct the name? We've got the individual names. Now we need to construct it. So we do it, the substituents are alphabetically positioned. So we're first going to start with the chlorine. So that's going to be 4 chloro, then D, then M. It's going to be, notice the hyphen, 3 methyl, and then butanoic acid. Akshay.
So could you put a halogen in a methyl group?
Yes, you can. The naming is much more complicated, and it sits in first year university. So in the NSC syllabus, we don't put substituents. We don't have indented substituents. So we don't have substituents within branches. All right, you definitely can. All right, there's no limit to how many levels of indentation. Well, there are limits, but I mean, you can continue to indent, especially if you're dealing with very, very long, big molecules. Noah.
So when the HO thing O is on the first carbon, do you not have to show that it's on the first carbon?
No, good question. No, you don't have to state that it's 1. You don't have to say butane 1-oic acid. It's a good question, but you don't need to. Because we know that the butanoic acid is carbon 1. It's on carbon 1. Good question. You wanted to ask a question, Alan?
Well, can I further expand on this question?
Sure.
For example, can an acid be on like a secondary carbon, like for example on carbon 3?
So let's assume you have a monster carbon backbone and you have a branch that has actually got carboxylic acid on it. You can have it. Now, what is DNA? Deoxyribonucleic acid.
That is something I do know.
Okay, you know DNA. DNA, deoxyribonucleic acid. So, sorry? So a DNA molecule is exceptionally long. But along that molecule's backbone, on there you can have acids and all sorts of other like amine groups, NH2s, etc. So yes, there's no limitation on that. Guys, we do need to move on. One last question.
Can you have
Yes.
an acid group on either side?
Yes. I knew I was going to say yes because there's so many. It's a beautiful question what you're asking. You're asking, can you get dicarboxylic acids? You absolutely can. And if you take, and I want all of you to please pay attention to this. If you take dicarboxylic acids with Cu groups on the end, and you react them with diols, where the hydroxyl groups are on the end, drum roll, you get polyester. Now the plastic, polyester, when you take a carboxylic acid and a alcohol, as you're going to see next week, the compound that's produced is an ester. If you use dicarboxylic acids and diols, then you get polymerization, where you get these exceptionally long molecules with those formula units that have repeat. Absolutely. Right. This is the thing with organic chemistry, ladies and gentlemen. There is no limit, really, to how long molecules can be and the level of complexity of organic molecules. That's why there are way over 13 million organic compounds, and we continue to add to it, as opposed to, I think it's 200,000 or 300,000 inorganic compounds. Right. Have any of you ever seen the movie Lorenzo's Oil? It's a true story. It's a beautiful, beautiful movie. It's about this little boy, Lorenzo, has got a problem. I forget what his condition is, but his dad goes and studies organic chemistry in order to figure out this. He's looking for this oil that will help his child. And he sits in the library with all these organic chemistry books, and he uses paper clips to actually work out, using biochemistry, what his son needs for this particular condition. And eventually he gets it, and then he actually finds this organic chemist that actually is able to, using fractional distillation, pull it out and isolate it. And it's called Lorenzo's Oil. It didn't save his son, but it helped other children who had that condition. It's a beautiful movie. Nick Nolte plays in it. And it's a true story. All right. Now, ladies and gentlemen, let's move on. We are going to jump esters. We're going to jump across esters. We will come back to them next week. Now, what I want us to do is I want us to look at aldehydes, and I want us to look at ketones. We've got about 15 minutes, and that is enough, because this is actually pretty easy, right? So aldehydes and ketones have the carbonyl group. So aldehydes and ketones both have the carbonyl group. Now the carbonyl group is C double bond O, right? So your carbonyl group, carbon obviously has a valency of 4. So when we talk about the carbonyl group, we are saying that you've got a carbon, there are 2 bonds there, and there are 2 bonds there with the oxygen, right? That is known as the carbonyl group, right? There we go. That is the carbonyl group. Now, you find the carbonyl group in the carboxyl group, the Cu group, C double bond O, OH. But now we are going to look at two options. The one is known as an aldehyde, the other one is known as a ketone. And those of you who do biology should have already come across them in metabolic processes. Have you? Have you? Okay. Maybe next year, because you guys, we're doing this in grade 10. Right? Who does life science here? All right. You will, metabolic processes produce aldehydes and ketones. So now let's talk about aldehydes. So aldehydes, in aldehydes, the C double bond O group is a carbon at the end of the carbon chain. So when you are dealing with an aldehyde, you are going to have this structure, right? And the suffix that we use is Al. Al. Aldehyde, Al. Right, so let's take a look at the homologous series of aldehydes. The R in here represents a hydrocarbon chain. Now we do ask you to draw the structural diagram of specific functional groups. Right, so let's go here and we start with C, double bond O, but now on the end we're going to have an H, and here we're going to have an H. So looking at this is going to be meth, okay? Now, we say the suffix is Al, but it's anal actually, all right? Anal, and we're not going to laugh at that, all right? Okay, so it's methanal. So the suffix is methanal, all right? So because it's an aldehyde, we use the suffix ANAL, methanal, right? Now, notice that there's a hydrogen on the end. Okay, you can look at it either way, it's symmetrical. If we now go to ethanol, right, we're going to have the double bond there, right, and we're going to have the H. On this side, we're going to have CH3. 1, 2, 3, 4, 1, 2, 3, 4. Always do the circle test when you're drawing. All right, that is going to be F and now. We do not need to number it because it's carbon number 1 is where the carbonyl group is. So this will be 1, this will be 2. Okay, so if you had to start adding double and triple bonds, then you start to have to work with the priority listing outside of our syllabus. So when you do get this, it's a good question because I'm going to give that to you. You are not going to get double bonds in the backbone. You will get substituents like methyl or ethyl groups and halogens. Okay, so, but then this is 1.
Would it just be the same concept as the example?
Exactly the same concept.
You just like numbers.
You start with carbon 1 where the carbonyl group is for aldehydes. Okay. So now, can you please draw for me propan? Now, please draw it for me, propanol. I have purposefully started the other way around. So this is going to be carbon 1, carbon 2, carbon 3. Yes, Josh?
For the substituents, what's the maximum?
Let's just get to this. Let's get to the substituents just now. Let's get to the substituents just now. We'll come back to the substituents. Let's just first just get this under the belt. All right? Are we okay with this? All right. Can I please ask you to draw the condensed structural formula? What did you get for your condensed structural formula? For the first one?
CHO.
So did you get H, C, OH? Did you get that? Ladies and gentlemen, that's wrong because that's an alcohol. That isn't also wrong. Also wrong. All right, it's fine to be wrong. It's okay to be wrong. The way we do aldehydes is as follows. H, C, H, O. And that tells us it's not an alcohol, it's an aldehyde. When you put the H before the O and between the C and the O, that tells us it's an aldehyde. Are you back? Yes. Sorry, just speak a bit louder, please.
The H in the front of the C.
Yeah, that comes from there.
Oh, okay.
But I represent this by not making it look like a hydroxyl group is by putting the H before the O. That tells you it's an aldehyde and not an alcohol. So the next one would be CH3, CHO. Okay, CH3, CHO. The next one would be CHO, CH2, CH3. Or CH3, CH2, sorry, let's just go back there, let's be consistent. CH2, CHO. Right. So the CHO you need to remember, yes.
So in the notes it said that the carbonyl groups always at the end of the chain.
In an aldehyde. In an aldehyde. I'm about to now go to ketones. In an aldehyde. It is at the end. Yeah. Now, what if we now move the C double bond O into the chain? In other words, the C double bond O now is not at the end, but is inside the chain. Right? So you can't have a 2-carbon ketone. Your smallest ketone has got 3 carbons. Because if there's 2 carbons, it's always going to be an aldehyde. So therefore, ladies and gentlemen, see here, you've got 2 carbon chains on either side. Now, let's take a look at that. So if we now go C, 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 and there's our carbonyl group, then on this side we've got 1, 2, 3, 4. 1, 2, 3, 4. On this side we've got 1, 2, 3, 4. Then how do we name this? Right, so what we do here, we say meth eth prop. So this is prop anone, propanone. And that one comes from ketone. Nowadays, you can't assume that only women use nail varnish. Who of you use nail polish remover? Acetone. You know, acetone is a ketone, just a different naming system. All right, so what if now we have this? 1, 2, 3, 4, 5. Right now, we have our C double bond O there. And we have 1, 2, 3 hydrogens there. 1, 2, 3, 4. All right, we're almost done. 1, 2, 3, 4. 1, 2, 3, 4. But now I put a fluorine there. 1, 2, 3. Right, now I've put a substituent in, and now, Josh, I'm going to address your question. All right, your question, I think, was asking what's the maximum amount of substituents you can put in?
In terms of the meth F, do they do
Oh, okay, with alkyl groups, you can do a lot, but we're going to go up to meth F propyl. Okay, with alkyl groups. That's the limit in the NSC syllabus. So we've got literally 2 minutes left, so I want to do this. And then I will post homework for you to do for the next lesson. All right, so let's take a look here. There's our chain. Now the carbonyl group dominates. So we're going to number from right to left so that the carbonyl group is on carbon 2 as opposed to carbon 4. Okay, so this is going to be meth F prop but pent. This is going to be pent and 2-one. Pentane 2-one. Okay. Meth F prop but pent. Pentane 2-one. And we're going to have 4 fluoro. Thank you very much, ladies and gents. I will post homework for you. It won't be that much, but I will post it so you can practice aldehydes and ketones. Thank you very much.